Welcome everybody to this session. As you may have noticed, there was a bit of discrepancy in the agenda, and we decided to wait a little bit as people were continuously dropping in. So we do everything with a shift of 10 minutes. This session is basically like following up with the morning sessions on LMPs, LMP technology, and we now talk about everything which comes beyond LMPs, further technologies and further applications which could become relevant for next generation RNA nanomedicines. And I would give a very short overview. So I changed a bit the content of my slides as I saw we are very limited in time. And so I give you just some snapshots of ideas and things we are doing without going into any detail, but just give you some starting points to consider what could be useful. That's our University Mainz. So RNA therapies, here we have, of course, famous Kati Kariko by now, my former colleague, who described, together with Hugh Weisman, first time the modified mRNA. You see the mRNA, how the community rather likes to look at it. So there's this different functional elements in the RNA, and it's drawn as a long block or a block of different components. And I would like to change the view about that a little bit by just saying I'm taking now the RNA just as a polymer, a polyelectrolyte, as I'm much too stupid to understand all of this RNA modifications. And so it's a highly charged biopolymer, which I can describe by physical methods, persistence length, folding, compactness, and so on. And so I also consider an established nanoparticle, pharmaceutical nanoparticle system, liposomes, which are complex with the RNA. And then I come to something which is organized, which is a nanoparticle. In the last 2 days, we heard lots of different terminologies. Is it nano or not? Is it complex? You could also call it a colloid or soft matter, whatsoever, all is justified as you like, but I would try to give you the viewpoint from a biophysicist's perspective to get a better understanding of that systems. Okay, and just to introduce what we are talking about, where we are starting from, to the right you see the cartoon of the LMPs, which everybody knows. There are systems which are called lipoplexes, known for much longer time, since the 90s of last century, from the times of gene therapy, which are similar but not exactly identical, but which are also useful maybe to be considered. And the idea is what is useful for us and what can we apply for our pharmaceutical applications. And one approach is to get understanding of the systems, to investigate them and to reveal certain coherencies in that. And here structure is one parameter which is of course very important. What you see here is an extract from an LMP work where we did small angle X-ray scattering and investigated systematically variations of certain cationic lipids and helper lipids, and found that there were some interesting counterintuitive observations on correlating structure and activity. This is plotted here. I can't explain it, but if you're interested, look at it. It's an approach which is not the usual screening one, but where we try to allocate certain molecular motifs with activity properties. And further to another snapshot of what can be done and what could be useful in the future is characterization, more characterization, not only X-rays. This is flow field flow fractionation. So it's a method to separate particles according to their size, or diffusion coefficient to be correct. And here you see results from a lipoplex formulation. You see this 2 peaks, a small one, this is free RNA. You see a big one, this is the lipoplexes or the lipid nanoparticles. And you get lots of information on that, like the size by different methods at each individual elution time, the RG to RH ratio, which gives you shape information and so on. So that's already very good. As you see, you can get information also on regulatory important parameters like free RNA. You get nice profiles. But the disadvantage is that it's still a qualitative method. And one thing to expand this is to use quantitative methods in combination. And what we did is to combine field flow fractionation with small angle X-ray scattering, which is an intrinsically quantitative method. So per se, X-rays can give you the absolute amount of scattering material, X-ray scattering material in the sample. And by that, you can quantitatively analyze the samples. You get the absolute fraction in microgram per milliliter of each individual particle size fraction, and you get information on internal structure, morphology, shape, and so on. We also like to expand it to parameters which we call fractal dimension, because we could correlate that with activity, so you get lots of quantitative information. I think this is something which has the potential to be regularly applied for many, many different nanoparticle systems, liposomes, lipid nanoparticles, polymer particles, and so on, because it's quantitative as it is, and it can be then correlated to lab methods. Something else, polymers. So most people talk about lipids so far. The polymer people say, oh, we are also there. So they were left a little bit behind in this COVID hype. But this is an interesting system because you can do other things with polymers as you can do with lipids, particularly with soluble electrolyte polymers, because the lipids are kind of amphiphiles. They aggregate, they self-aggregate in a different manner than these polymers. And you can do then studies, and this is a very simple physical-chemical experiment where you mix the different components to each other. What has been found is that if you add a large excess of polymer to the RNA, you find a new phase of RNA complex with the polyethylenimine, and you can show that it has very high transfection efficacy in vitro and in vivo, and yet the activity increases by the excess of PEI of the polymer. Now you could say, of course, there are these descriptions of pi excess being useful for activity, but it's something else. So that's all biological activity. We skip that for sake of time. That's again our AF4 method. And what you see is, if you separate according to size, you get different oligomers with repeating molar mass, which corresponds to something like a single mRNA complexed molecule. And so this means somehow we could now form a formulation where individual nanoparticles consisting of single RNA molecules exist. This has also been proven by X-ray scattering. You see the X-ray scattering curves to the left and the what we call pair distribution functions to the right. What comes out is that the RNA is extremely compacted, very small, with certain advantages for delivery. You can now reach compartments which were not accessible so far, and you can functionalize and everything. What's the foundation? It's basically polymer physics. So it's a polymer electrolyte complex where the aggregation conditions depend on the concentration and on the relative concentration of the moieties. So what we do is we provide a large excess of PI and a very low concentration of RNA, and by that we saturate the large RNA molecules with the PI, and we then increase on the first hand the number of particles, and we make them smaller, both favorable for activity for certain applications. So with that, I would like to stop and leave it to the others, but so the message and also the topic for this session: we need tailored systems according to certain applications. LNPs are great, but maybe they are not suitable for everything. If we improve our control systems, we may get much faster and much better development towards such systems. And we should also look at more platforms. I just showed you lipids and polymers. There are more solid particles, silicon nanoparticles, everything. We should consider them. And for this polymer condensed RNA molecules, this is something interesting from a basic science perspective because they are so small and so compact, and as well of interest for novel RNA therapeutics for various applications, vaccinations, and much more. So with that, I think I just in time, I would like to stop. This is the acknowledgements to the teams who contributed, and I would not like to go into deeper details. Here you find my contact information and the summary of some publications I mentioned or almost not mentioned.